welcome to QuBites, your bite-sized pieces of quantum computing. My name is Rene from Valorem Reply, and today we're going to talk about noisy quantum systems. And I'm very honored to have a special expert guest today, Dr. Christopher Grenade. Hi, Chris, and welcome to the show. How are you today?
I'm doing great. Thanks for having me here.
Can you tell us a little bit about yourself and your background as it relates to quantum computing?
Yeah, so I started, really getting interested in quantum computing a little over 10 years ago. Started learning, oh, hey, there's this area that really intersects between physics and computer science and math and all these other things that I love. Um, and it kind of gave a neat idea of like, there's a different way of computing than classical that might tell us something about what kinds of computation are possible in the universe. And, that's a little bit high minded and everything, but it was a lot of fun kind of learning about different parts of complexity and how, quantum computing really challenges a lot of assumptions there. Um, and based on that, as an undergrad, started pursuing a master's degree and a PhD in quantum computing, um, and then did a postdoc at University of Sydney. And about 4 years ago, um, joined Microsoft as a research software developer, and I now work on Quantum Development Kit, in particular, Q language, libraries, things like that. Work a lot in those areas, and it's been really neat to kind of see that sort of come back to a lot of what interested me about quantum computing, in the first place, and putting the software tools out there to help explore and understand what quantum computing really is and make the most of it.
Got it. So let's dive into today's topic. And in QuBites season 1 and 2, we already talked with Dr. Sarah Kaiser, who's also the co-author of this amazing book, Learn Quantum Computing with Python and Q Sharp. A hands-on approach, right? And it's out now since June, I think. And of course, I have the copy here, which I paid for myself, folks, right? So this is not an advertisement, right? And but this is an advertisement in the sense of that I'm just going to highly recommend this book. I started to read it. It's fantastic. And so Sarah Kaiser, which you know from previous episodes, and finally we also have Chris. So can you show? I'm sure you're happy now about that it's finally out, right? Because I can imagine it's a lot of work. This book. It doesn't look that thick, but folks, this is amazing content in here. Definitely get a copy. Anyhow, what has happened since the release? Any other feedback and comments you received so far?
Well, I mean, first off, it's been really wonderful and just very humbling to hear, all the amazing and kind words, such as what you've just shared. So thank you very much for that. Um, but, I mean, I think the other that has been really neat to see is quantum computing hasn't stopped moving when we put out the book, right? A lot of things keep moving forward, and there's a lot of really neat, exciting developments that are continuing to be made, and Q sharp as a language, the libraries for Q sharp. I think one of the things that's really excited me in the months since we put that out there, and what I love to talk about in a follow up, would be quantum intermediate representations. So really using LLVM, using everything we've learned about classical compilers and tool chains and how to represent classical programs, taking that and applying it to help solve some pretty difficult problems with running quantum computers on real, actual scalable hardware. And so seeing the progress in that area has really been exciting to see. As far as feedback, as mentioned, I think it's been really amazing to hear all the kind words. We really wanted to try and make quantum computing more understandable. Um, to kind of not make things more weird or mysterious, but just actually talk about quantum computing. And so that's been really
Right.
neat to hear, um, hear that. But I think the other thing that I didn't really expect that's been really neat to hear is that our book has helped people, realize, oh, hey, I can use Q Sharp along with whatever tools I already know and love, like Python. That
Right.
there's I think, a kind of tendency to think, oh, hey, quantum computing means I need a whole new tool set. I need to give up
Mhm.
everything I know. but I really think of it more like, a GPU or something like that, where I might write in CUDA or I might write in OpenCL, but that's part of a program written in Python or whatever other language I already know. Um, rather than reinventing the wheel, it's something that works well alongside. And so hearing that our book has really helped address that and invite people in who are using Python and loving Python, that's been really neat to hear.
Awesome. Yeah, and I can only just reiterate, get a copy. It's amazing. Um, it's you made a great point about looking at quantum computers more, let's say, like an acceleration chip, like a GPU kind of a thing, right? It's giving us extra power, and because like there's a lot of misconceptions still out there that couple of people still think like quantum computers are going to replace our classical computers, right? Like, folks,
Yeah,
this is not going to run a quantum computer. Like, you will still have classical computer, you will still have semiconductor chips. All of that is still needed, and so I love how you phrase it, like saying basically quantum computer is almost like a GPU, like an accelerator chip, another extra thing I have for certain specific tasks to compute
right.
better and faster for these certain specific tasks. And so to reach this, and that we actually have, well, good quantum computers in the end. I know you also work on this quantum computing research field in the control and simulation of these noisy
Mhm.
quantum systems, right? And of course, it's very important for error correction and prevention in the end as well. So, can you explain why noise plays such an important role in the quantum computing systems, and why error correction and prevention is key for, well, achieving the true quantum advantage, basically meaning that quantum computers are outpacing classical computers for
Yeah.
certain problems, of course. So, long question, but let's talk
Oh,
about noise.
but I think you set that up beautifully because, it's right there in, like, talking about advantage for certain problems, right? Because if I go all the way kind of back to, what quantum computing really is, we don't expect, as you say, like, quantum computing will replace your phone or replace, kind of your web browser, right? That there are tasks for which quantum computers will simply never be better than corresponding classical computers. A lot of what we do in, quantum algorithms and quantum applications is find areas where, for specific problems we get a lot of speed up by using a quantum computer. um, on the other hand, if there isn't a particular speed up, then we're just stuck running the classical program but on a quantum computer, and we really don't expect to see an advantage if we're
Yeah.
not actually using an algorithm that takes advantage of unique properties of quantum physics. And that gets back at noise because this is, at a very broad brush, what noise in a quantum system does is makes your quantum computer behave more like a classical computer. And in its most extreme, I can't actually run any of those algorithms that really give us that advantage
Mhm.
if there's too much noise or if I'm running an algorithm that's too sensitive to that noise. Um, and then longer term, we know from things like the fault tolerance threshold theorem that there is a good enough that we can get noise past that really helps us address that longer term. But if you're sitting, running on hardware today, running
Mhm.
near term algorithms on what's currently available, noise is a part of life. And that's something that you have to deal with and understand as an algorithms developer so that you can use error correction, you can use error mitigation, or you can use and write algorithms that are inherently more robust to that noise. Um, and understanding noise and studying it and simulating how noise affects your programs helps understand how how that noise will affect the output that you get. And so I think that's really ties into that broader story of how do we reach advantage to be able to understand the effect that noise has in getting there.
Right. Makes a lot of sense. Thanks for that excellent explanation. Still, it's a limited availability of real quantum computing hardware, right? So it's still like real quantum computers are still very much in its infancy. Actually, getting access to one, even though they're in the infancy stage, basically, is very hard, right? To get access to real quantum computing hardware. Fortunately, there are services like Azure Quantum, for example, where you can basically rent computing time on a real quantum computer via the cloud. It's a
Hmm.
super fantastic model, in fact. But anyhow, like in order to solve these challenging problems, and with noise and so on, and like you said, like making developers or algorithm developers aware that they need to think about
Hmm.
noise correction and so on. It's also important to simulate noise for quantum computers because we don't have enough quantum real hardware there, right? So we need to simulate noise as well in order to simulate properly for the real quantum computer in the end. And so this is now
Absolutely.
possible to basically simulate noise with quantum computing algorithms. And you mentioned that you also work on the Azure QDK, the Azure Quantum Development Kit,
Mhm.
and there's a noisy simulator in there, right? And can you tell us a
That's
little
right.
bit about that exciting feature and what does it do and how can it be leveraged?
Absolutely. So we're really excited to have put this out there a few months ago for in preview for people to try, give us feedback, see how things work. But the QDK now includes an open system simulator. That's uh, another way of saying a noisy simulator that lets you attach a noise model that says, when I push the H button, when I call an H operation,
Hmm.
actually this other object called a quantum channel happens instead of the ideal H. And then you, as a developer, can take and attach a noise model that describes what should happen when you press an H, call an H operation,
Hmm.
and then run the same programs that you run on the standard typical full state simulator that simulates an ideal quantum computer and
Yeah.
see how your outputs change on when you're running against that noise model. And that
Hmm.
lets you do a number of things. And as you said, that lets you predict how things will work on hardware.
Hmm.
Maybe not perfectly. It's hard to really learn exactly what noise works on the quantum. It is affecting your quantum computer, and the process of learning that, there's a whole field of research that, as you allude to, that was a lot of what I did my PhD in, called quantum characterization, verification, and validation, sometimes under the acronym QCVV. But that's how you learn what noise models apply to your system. Um,
Hmm.
but it, but having a noisy simulator not only lets you take the noise model that you've learned through something like QCVV and run your programs against that, but it also lets you hypothesize what a different noise model might look to say, if I had a qubit that was this good, this high fidelity, what would I see? If I had a
Hmm.
qubit that was worse than what's there in hardware. And that's really important because it is a moving target. We keep seeing better and better hardware. You mentioned the really exciting hardware available through Azure Quantum today. And I could barely even imagine noise rates that low from, all of the experience I had, you know, s- talking to experimentalist friends like 10 years ago. It's night and day. We've really come a
Hmm.
long way, and there's a lot less noise and devices now than there used to be. So maybe back then I would say, "Hey, let me go simulate on a noise model that's impossibly good. No one could ever get." And then we got there, right? Because things keep improving. Um, so maybe I'm here sitting today, I'll want to simulate how an algorithm works on even lower noise, or noise that might look a little bit different, that's more coherent or more incoherent. And having the ability to set those noise models really lets me do that exploration as a quantum developer to see how different noise will affect my programs.
A very important topic that we haven't covered in our show so far, and that you don't hear very often, actually. Um, but like you said, it's so important because, like, typically when you have a simulator, it simulates the ideal state, but that's not how the real world works, right? So injecting noise and simulating noise so that it's more closer to how it would actually execute a real quantum computer that, of course, has noise is super
Mhm.
important because otherwise you might get crazy. You might scratch your head, and debugging, well, that's a whole different
Yeah,
story, right? And so yeah, no, super important topic. Thanks so much, Chris, for joining us today and sharing all your insights. That's very much appreciated. Thank you so much.
absolutely. And thanks for having me here. Really exciting to talk about it and, hear all y- your kind words. I really appreciate it.
Well, thanks everyone for joining us for yet another episode of QBites, your bite-sized pieces of quantum computing. Watch our blog, follow our social media channels to hear all about the next episodes. And of course, take care of yourself and your loved ones, and see you soon. Bye bye.